All right, good day. It is currently evening of Sunday, but I suppose that's not very relevant. For this video series, I want to get through I want to get past the whole of topic 5 so that at the very least anyone who is trying to, um uh, get their grades up for quiz 3 and maybe for the finals, you can review all you want for topic 5, okay? Thing about topic 5 and the rest of quiz 3 is that I believe it's the easiest because, well, as you will see later on, you will know what to do. It's just that you have to do it. Right? So for the lazy people here, like me, it's not going to be the best time because it's very tedious. Some of the problems are going to be tedious, but at the very least, you will know what to do. It's only up to you now if you want to do it or not. Right? So let's begin. Right, this is steady flow devices. We'll talk about steady flow work first. Right, we'll talk about the things that change from non-flow systems or from closed systems to open systems, and we'll talk about the different kinds of steady flow devices. Right, this first part will tackle, of course, steady flow work. Right, the next part we'll go part by part or type by type for steady flow devices. All right. So, studying thermodynamics is a way for scientists and engineers to manipulate the physical world to achieve their goals, right? The last time for quiz 2, right, we've talked about the first law of thermodynamics, and basically that is a way now to describe, right, how things or right, how energy moves, right, and that energy is conserved, right, no matter what. And we had this little footnote that technically you can create, quote unquote, create energy because of nuclear reactions, but we're not chemical engineers, we're not nuclear engineers, we're just mechanical engineers who are dealing with hot steam. So, yeah, right? This is now our way to understand how the world works, to achieve our goals, and well, we'll understand the world even better because this is our bread and butter, right? Steady flow systems. Right? Before we begin, I'd like to offer this quote: engineering is an activity other than purely manual and physical work, which brings about the utilization of the materials and laws of nature for the good of humanity. Right? This is by Rudolf E. Helmond. Right? I think he was a German engineer, or maybe he was the economist. No, he was the German engineer. Yeah, I'm pretty sure. But yeah, I had this small aside in our classes before that if you went into engineering, if you went into mechanical engineering thinking that this industry has a lot of money, well, I'm so sorry. I don't think I don't agree. Right, the current inside jokes that we're currently seeing, right, that we're seeing around, let's say, for example, what Facebook pages, ask around with older, maybe if you have seniors that you know already, maybe seniors or fresh grads who are also engineers, ask them about the job market, they will say it's atrocious, right? However, right, if you're in engineering because, well, the way you believe you can help people is through the art and science of engineering, then well, you're in the correct place, right? Engineering is ultimately to improve the quality of life of not only yourself, maybe your loved ones, maybe your greater community, maybe just the whole of humanity. Okay, so we'll talk about how we as mechanical engineers we are able to indirectly power the world, right? Indirectly, we are responsible for the movement of, I don't know, vehicles, right? For the comfort cooling of millions and billions of people around the world through steady flow systems. Okay, so let's start with open systems and steady flow work. Right now with quiz 3, we are going into open systems. Right, we are now allowing ourselves to discuss, right, the mass of not only the transfer not only of energy but also mass. Right, in topic 4 we discussed not only the ideal gas laws but also, right, the conservation of mass. And so now the gate is open. Right, we can now talk about combining the first law and conservation of mass together. Right, speaking of the first law states that energy cannot be created nor destroyed. Of course, we know this. It can only be transformed from one form into another or transferred from one body to another. In math terms, you can say Q minus W is equal to delta E. Right? In topic 2 or in topic 3, I said that delta E takes on two forms, right? Either delta KE plus delta PE plus delta U for closed systems, or now, because we're talking about open systems, that will be delta KE plus delta PE plus delta H. Okay? And so this is now one of the most important equations that you will need in topics 5 and 6. Right? Okay. Now, the thing about this, back from topic 2, I think, right? Topic 2, we said that in this subject, we characterize work as inducing the motion or deformation of a system. Oh, actually, this is topic 3 because work is a part of energy transfer. But suffice to say, right, work is just inducing the motion or deformation of a system. Basically, if something moves, right, or something deforms, that is already an indication that work has been done, or has been done on, or has been done by the system, right? Back in quizzes 1 and 2, we were talking about closed systems, right? Non-flow work, right? So we've been talking about all this time piston cylinder assembly, so on so forth. It's just the same thing over and over again, right? And hopefully it has been hammered into our brains that if this closed system is going to compress, right? There's going to be less volume, right? That will be negative work. That work goes into the system. However, right? If the system now expands, that is now expansion, that is now work out, right? So that will be work is being done by the system, right? So this is work out, right? And this is work in. Now, we're talking about open systems, right? And with open systems now, it is no longer about deformation, the deformation of a system, because, right, for many open systems, the boundary is what does not change. If you notice in here in closed systems, the boundary is very pliable. Pliable in the sense that you can change it if you can compress or you can expand the fluid you are working with. However, for open systems, the boundary remains the same. It remains this invisible box that you're seeing here, right? As opposed to this piston, right, that we are seeing on the left-hand side. The right-hand side is that of an engine block. The engine block takes in air with it, right? It takes air in, right? It takes fuel in. It combines those two. It makes the boom boom sounds. It combusts this air fuel mixture, and then that is responsible for the work. The work which is manifested by this rotation of the drive shaft. That is what allows your car to go, right? And of course, the air in and the fuel in, once they mix and then they combust, right? They become exhaust gas, right? And that exhaust gas goes out as well. So you notice there's a kind of conservation of mass happening as well. The thing about this is that the engine block itself, unless, I don't know, it explodes, right, is not experiencing any kind of expansion or compression, right? If anything, the work, right, you only know that work has been done by the system because this drive shaft is spinning. And so now, when you are thinking of something and you are thinking, does this process or does this thing or does this device have any work transfer, you just have to ask yourself the question, is it moving, shaking, vibrating, rolling, whatever, right? If it is not doing any of those things, if it's just stationary, there is no work. Okay. All right. So, right, that was our quiz 2. And this is now the, what do you call this? The coverage of our quiz 3. Right? Okay. And so, we go back to the original, the definition for work, right? Last time we said it was force times displacement. We were able to manipulate that equation because of the fact that you're working with a fluid and now you're able to turn it into pressure times volume. But we know it's more complicated, right? We know that for us to understand how much work has been done, you need to know the path. Right? You need to know the path, or basically work is not a property. Just because you know the initial state and the final state does not mean you will know the amount of work that has been done. You also need to know the process from which the initial state goes into the final state. So you know the work. Okay? Here we have the work non-flow formula, or rather the differential form of the work non-flow formula. Basically, right? I know if anyone else outside of class is going to see this, I will remark this now. This should be a delta instead of a D because technically work is not a property, but right, I don't want to I don't want to get into the nitty-gritty of these things, right? This still functions as a differential, right? So that means that when you just want to get the work non-flow, it is going to be the integral of PdV from the initial to the final volume, right? Because you are integrating based on volume. Okay. The thing about this, though, is that this only works for non-flow systems. There is no way for us to compute work in steady flow systems naturally. We're going to have to find ourselves a steady flow work formula. And so how is that going to work? Well, how is that going to work? Anyway, right, we are going to go with the first law of thermo for closed systems, right? This is for closed systems. That does not mean it's now untrue. It's just for closed systems, right? For closed systems, what usually happens is this. Let's not go over there yet. We have Q minus W is equal to delta KE plus delta PE plus delta U. What I will do right now is that I will get the differentials of everybody, right? The differentials of everybody, and also we have to recognize that your delta KE and your delta PE are just negligible in this case. In a lot of cases, they are now negligible, so we can just cancel, right? They are negligible. So we can cancel them, and we will just get the differentials of everybody else, which means dq minus dw, and because this is for non-flow systems, this is for closed systems, we can write down here nf, and you will just get here du, right? So we will have this. Okay. All right. Cool. Now, the thing about this is that I can now turn I can now turn the differential version of the work non-flow into your PDV, right? So because we said earlier that this is just equal to PDV, we can just say, oh, PDV is equal to du. That's going to be important later on. Now, what we will do is that we will stock this, right? Let's call this equation 1, right? And let's look at somewhere else. The next thing that we're supposed to look at is the relationship of H and U. The general relationship of H and U is supposed to be H is equal to U plus PV. And now what we're going to do again is we're going to take the differential of both sides. We will get dH is equal to du plus the differential of this thing, P times V, the flow energy, right? This is our flow energy. Flow energy. Right? And with this thing, you already know what's supposed to happen, right? This is a product of two different variables, and these are two different variables, right? It's not that one is constant, the other is a variable. Both of them are variables. So we will do the product rule. dH is equal to du plus, right? F prime G, Fg prime, PdV, and then VdP. Okay. Now what? Right? Notice that what we can do is we can isolate our du. Why would I do that? It's because, look at this. For equation 1, the right-hand side is du, so I might be able to equate the two, right? Let's try and move both of these terms to the left. We will have du is equal to dH minus PdV minus VdP. That is now our equation 2. Okay. So we will have that, and that. Now, we can just bring these two together. Let's see that in action, right? If we equate 1 and 2, equating du, right? We will have, on one side, we will have dq minus pdv, right? This is from equation 1, is equal to dh, right? Minus pdv minus VdP. And notice that you have negative PDV on both sides. You can just cancel. And what we can do is we can move this negative VdP to the other side. You will have dq plus, right? Because this is negative. This now becomes plus VdP is equal to dH. Let's call this our equation 3. Why is that necessary? Because, well, this is going to look very familiar, right? This is going to look very familiar. Now, we take the first law of thermo for open systems. If this form is for closed systems, now we take them for open systems. For open systems, we just replace everything in here with a delta H, right? And we replace the delta U with the delta H. We will have Q minus W is equal to delta KE plus delta PE plus delta H. And now again, we say, these guys are negligible. Negligible. And now we take the differential of both sides. We will get dW minus, this is now for open systems, so steady flow is equal to dH. And now compare equations 3 and 4. We'll go back to the presentation. We'll have this. And if we substitute du, right, we will get this. Now notice these two. Right? This is basically equation 3 and equation 4. They're basically the same. And they are the same. Right? They're both true. That's what I mean. That means if they're both true, then we can say that these two highlighted terms, negative dWSF and VDP, are the same. Comparing, right? Comparing 3 and 4, we will now get to the conclusion wherein your negative dWSF is equal to your VDP, which will mean that your dWSF is equal to your negative VDP. Notice the similarity of this to this thing. Or where is it? This thing, right? dWNF is equal to your PDV. Now, dWSF is now equal to negative VDP. Very interesting. That means that our work steady flow is just going to be the integral of negative VDP from the initial pressure to the final pressure. Right? There you go. And so now that we are armed with this information, right, we can proceed. The thing about this steady flow work is that, well, it is now in terms of pressure, right? It is now in terms of pressure. So we just think about things in a slightly different way, right? Notice that, again, right, the amount of work does not depend on its endpoint. Work is not a property. Notice that in this PV diagram, the P is the y-axis, right? It's the vertical axis. And then V is the horizontal axis. It's like the x-axis, right? For those who have gone through Calling 2, right? Basically integral calculus, right? This thing, say for example, we have this process right here. We have this curve, right? And this is the process that takes state 1 into state 2. This, right? This, what do you call this? This area, right? This area under the curve is what? Right? Notice that you can break this down into many little tiny rectangles, right? That rectangle is not very straight. But anyway, this rectangle has a width that is just a small slice of V. A small slice of V. Oh, this is dV. And notice that the value of the length of this thing is what? Wherever this is, or wherever the P is. So these are just little tiny bits and pieces of PDV. Oh, so this thing is just the combination, or rather the integration, of all of the little values of PDV, or in other words, this is the work non-flow. Now, I will ask you all, where is this work steady flow? The work steady flow, because it's now VDP, it will now be the area to the right of the p-axis, this thing. That is now your work steady flow. Notice that this, you can break this down into little tiny, right? Little tiny rectangles, right? And then the width of these rectangles are little tiny slices of p, dp. And then look at this, where is this? Or what is the length of this? That is the length of your volume, whatever volume the state, or rather the substance, is currently in. Now you might say, okay, sure, whatever. Why is there a negative? Right? Okay. So to clear up things about the negative sign, notice that this from state 1 to state 2, what's happening is that the volume of your state, or rather the volume of your substance from state 1 to state 2 has increased. This is your volume 1 and this is your volume 2. Notice what has happened. It has increased. That means that your work is positive. Why is your work positive? Because based on the work non-flow formula, which is the basically PDV from V1 to V2, because you've read it from left to right, right? This is registered as a positive area, right? This is a positive area because you read it from left to right and because the area is above the x-axis. Right? If this area was below the x-axis, this would be read as a negative area. That would be weird because there's no negative pressure. But anyway, the only time this could be registered as a negative work, right, as a negative area, is if these were reversed. Or in other words, if your V1 is bigger than your V2, that would mean that you made the volume smaller. And in that case, the work non-flow would be registered as a negative because you've now read it from right to left. Right? This is now your negative, and then this is now your positive. Now, let's see what's supposed to happen for the work steady flow, right? Why is there a negative in here? Well, in this case, you can still roughly, you can still roughly think about this as an expansion or a compression. Okay? What happens here is that there is positive non-flow work, right? Because what happened was that V1 expanded into V2. Notice what happens as well for the pressure. The pressure at state 1 was lowered into the pressure at state 2. There was an expansion that happened. That means that, well, this is now positive, right? This is now positive. Work was done by the system. Kumbaga, right? Or in other words, it breathed out. Right? So the volume increased, work was done by the system, and what do you notice happen? P1 to P2 is read from top to bottom, right? So if you think about it, wait a second, that's not the way it's supposed to be read, right? If you're going to think about this as an x dy, right? If you're thinking about this as an x dy, the y1 and the y2, right, need to be, this should be lower, and then this should be higher, right? For it to register as a positive kind of work. However, in this case, your P1 is higher. Your Y1 is higher than your P2. That would register a negative area, but because of this additional negative sign, your work steady flow is actually positive. It's positive because this is originally negative, and then they just put another negative sign. In other words, right, if you didn't want to listen to all of that math, this negative sign is here so that it works out the correct unit for your work, right? On the other hand, if now your work, or rather, if now your pressure increases, right? If now your pressure increases, what happens is that, of course, this is now registered as a positive work, right? This now registers as a positive area. And because positive times negative is a negative, you have now seen, oh, the pressure increased. Oh, it was compressed. Therefore, your work is negative, right? Okay. So that's it, right? The negative sign is there to account for the correct kind of sign for your steady flow work. Okay. Now, we will have here the sign convention. So just as I was saying earlier, when the system does the work, positive. When the system is, when the work is done on the system, it is negative. Or in other words, right, when the system expands, right, your work is positive. When the system contracts, your work is negative. The thing is, this is always true for non-flow work, right? In this case, it needs a little bit of an edit when it comes to steady flow work. I feel like the conclusion is no longer very it's no longer very cut and dry for steady flow work. What I think should happen in here is that instead of saying expands, because that's a little bit vague, when the system pressure decreases, right? Decreases, right? Your work is positive and contracts. I mean, like, kind of, I guess it's kind of the same thing, right? When your pressure, system pressure increases, that is when your work is negative. Because, well, essentially, you've compressed the system. You have done some work to compress the system, right? Us from the outside of the system. Okay. And now that we've said all of those things, we can now properly redefine, right, a couple of different things. Right? In thermodynamics, we usually analyze processes whose properties have explicit relationships between states. In other words, yes, there are formulas that are floating around out there, right, that take us from the initial to the final pressure, from the initial to final temperature, so on and so forth. But, right, the most what do you call this? The most useful, or perhaps the most efficient way to look at a system, or rather a process, is through the polytropic index. Right? The polytropic index basically states that any process, so long as it's polytropic, may be described through the statement PV raised to n is constant. So we'll be dealing with this part next, right? When your PV raised to n is constant, that means, right, when your PV raised to n is constant, that means that basically your P1 V1 raised to n is equal to P2 V2 raised to n. Say, for example, you have this little process right here from 1 to 2, right? If you have this process right here, oops, let's make it a bit more, smooth. Actually, any point between process 1 and 2 will still follow this will still follow this relationship. Say, for example, we have point A and then point B. They are still going to follow, right? We have PA, VA raised to n, right? Which is a little weird now I think about it, is equal to PB, right? PB VB raised to n, right? Anything along this process, because this process is polytropic, will follow those rules, or that rule in particular. Okay. Now, we'll just try and simplify it here. This is just 1 and 2. And then we will have our process. Right, there you go. We will go through the 5 processes. There's supposed to be 6, but I'm only going through the 5. 1, 2, 3, 4, 5. Right? Isentropic processes are supposed to be here, but they are not polytropic processes. So I'll just deal away with them for now. Right? We start with isobaric processes. Hopefully everyone remembers the work non-flow formula for isobaric processes. Right? We also hopefully know, right, the n for each one. Right? Okay, so actually, let's move everything a little bit. Let's move everything to the left. Yeah. Let's move everything to the left. And now let's have here a little table. Right? Let's have here a little table. The type of process is here. Right? The type of process is here. The type of n, or rather the value of n, should be here. Right? Let's make that color blue. And then let's have this as a, what do you call this? Let's have this as a red, maybe. Red here is the formula for the work non-flow. And let's make here purple, the formula for the work steady flow. Right? Okay. So we will have 5 different processes. We will have isobaric, right? Isothermal, okay. Let me just center that. And then this is going to be isentropic, and then this is isometric, and then this is going to be polytropic. Okay, now we have this, and hopefully everyone can follow along. The n polytropic index of an isobaric process is 0. For an isothermal process, it is 1. For an isentropic process, the n is k, your adiabatic index. Isometric, well, it approaches infinity. And polytropic index is anything else. Right? Anything else. Any other value of n will work. Right? And I suppose we should just put in here, isobaric, pressure is constant. Isothermal, temperature is constant. Isentropic, entropy is constant. Isometric, volume is constant. Polytropic, well, PV raised to N is constant. Okay, now we will go through the different work non-flows, right? For now, we will go process by process. So first we start off with isobaric processes. We have an N of 0, and our work non-flow is P times V2 minus V1. Let us now try and get, right? Let us now try and get the work steady flow for an isobaric process, right? And if we remember properly, and actually we see it right here already, right? The work steady flow, right? The work steady flow for any process is just going to be, right, the negative integral of, right, VdP from P1 to P2. P1 to P2. Let's go with isobaric processes. But now, let's stop and think. Wait a second. Isobaric means that, right? Isobaric means that your pressures are constant. So that means your P1, right? Thus, P1 is equal to P2. Let's just call that common P. So the work steady flow is actually just from P to P of volume times dP. So you might be thinking, wait a second, what is the integral of anything? I don't even care anymore what the relationship is between P and V. The fact that your P remains constant means that the bounds are going to be the same, right? No matter what kind of answer I'm going to get from my integral, I'm still going to, right? I'm still going to blah blah blah. I'm still going to substitute them by P and then by P, which cancels everything out, which means that, oh, actually the answer for this is just 0. That is the work steady flow for an isobaric process. Very interesting. Okay, and so now we will have just 0 apparently. Okay, very interesting. Next, right, we will have isothermal processes. Isothermal processes, this one has the weird one, right? The weird one that it breaks the mold, right? It breaks the general formula, as we'll see later, right? It has a polytropic index of 1, and basically its work non-flow is PV times ln V2 minus ln V2 over V1. Okay, so that is how we're going to do it. PV times ln of V2 over V1. Okay, now, right, if you've forgotten, right, this, what does this mean, right? Why did I forget to include subscripts, right? What is this? Are we going to use P1 V1? Are we going to use P2 V2? Either works, right? So it's okay. Either works. P1 V1 works. P2 V2 works. Just do not mismatch. This will not work. This will not work as well. Okay. Now, for isothermal processes, let's try and find out the relationship, or rather the work steady flow for an isothermal process. Isothermal. We will have here, temperature is constant. Basically, we will now manipulate our PV raised to N is equal to constant, right? It's equal to constant. Okay, so we will now manipulate this. This is now PV raised to 1. So PV is constant, right? PV raised to 1 is constant, which means that basically your P1 V1 is equal to your P2 V2. This is why, right, the PV right here works either state, right? Either state. Okay, let's now go through this. What will happen then? We need, right, when we write down WSF, negative integral of P1 to P2 of VdP, we now need your value of V as a constant, or sorry, as a function of P. What you can do is just divide P on both sides. You will get negative integral P1 P2 constant over P times dP. And this is going to sound very familiar, right? Negative constant times dP over P, the integral of dP over P from P1 to P2. And now you will say, oh, that's just another ln. constant, negative constant times ln of P from P1 to P2, and you say, oh, this is my new formula. My new formula is now negative constant. If you remember what a constant is, right? That is just going to be either P1 V1 or P2 V2. Let's just write it down again as negative PV and then ln P2 over P1, right? For those who are a little bit confused, this is just ln of P2 minus ln of P1. And because of the laws of logarithms, you can just pile them up like this, right? ln of A minus ln of B is equal to ln of A over B. So this is now our formula for the work steady flow of an isothermal process. Negative PV times ln of P2 over P1. So you might be thinking, wait, did he misprint this, right? Was this a wrong copy paste? Actually, no, right? So you might say to yourself, well, that's not what we got, right? We got negative PV ln P2 over P1. So now the only thing that's supposed to the only thing that this means, well, how am I supposed to say this, right? The only way that this is true is that if both of them are equal, are they equal? Let's try this out. Okay, so we are thinking, how can these two things be equal? PV ln V2 over V1, are we saying that it is equal, right? Is that equal to negative PV, right, ln P2 over P1? Because certainly I understand with the PVs, oh, okay, yeah, whatever, right? And then you will now come across ln of V2 over V1 is equal to negative ln of P2 over P1. But then, right, I will invoke a law of a logarithm, but that basically says, right, this is the superpower of the logarithm, which is if you have an ln of A raised to B, you can just drop down the B in front of the logarithm. Now, why is this important? It's because there's a negative 1 in front of this logarithm. What I can do is now force that back up in there. And when you are raising something to negative 1, you are essentially trying to flip the numerator and then the denominator. In this law of exponent, right, if you have an A over B raised to negative 1, what you're basically doing is that you are now giving the negative 1 to both sides, and you are now making them switch positions. And so, okay, fine, whatever. ln of V2 over V1 is now equal to ln of P1 over P2. What is this going to do? Right? And now you see, wait, both sides are just ln'd, right? Both sides are just ln'd. So technically, what you can do is just cancel the ln's. You don't need to look at the ln's themselves. You can just look at the things inside. And now, once you look at the things inside, you can, or I invite you to, cross multiply. P2 V2 is equal to P1 V1, and that should sound familiar because that is true, right? That is true. That is now true. Why is that true? Because that is the original constraint, right? That means that P1 V1, when P1 V1 is equal to P2 V2, that is an isothermal process, right? And so both of these, how should I say this? Both of these forms are possible, right? Both of these terms are usable not only for steady flow systems, but also for non-flow systems. This is still valid for a non-flow system. Say, for example, you only have P1, P2, and V1. You can still solve for your work non-flow. Okay? That is for an isothermal process. Okay? So we can write this down. Let's just copy paste this and then I put it here and then turn it purple. Okay? Now for an isentropic process, this one required a little bit of elbow grease, right? Let's go now here. For an isentropic process, your N is your K, right? That is the adiabatic index. Each substance has its own K, and technically that K might change based on temperature, but we're not that too deep into thermodynamics yet, such that we're supposed to care about it that much, right? But yeah, I've given you guys 3 values of k so far that you need to take into consideration, right? Your k can either be one of these 3 values, right? Either if your k, or sorry, if your gas, or sorry, if your substance, if your fluid is a diatomic gas, right? So if it's a diatomic gas, right? You can say that your K is about 1.4, right? So a diatomic gas is what? Like H2, N2, air, right? Air is a part of what do you call this? Air is basically a diatomic gas. It's a mixture of oxygen and nitrogen. What else? Fluorine, I suppose. That kind of thing, right? If your gas is monatomic, so basically, I don't know, helium, the other inert gases, helium, neon, argon, xenon, right? He, arcar, xenon, radon. So I'm just listing everything in this list now. Oganesson, if you want to, right? That is going to be 1.667, right? And then finally, and I don't know, right? If it's CO2 for some reason, it will be 1.3. And I've just discovered this, not discovered, but like I just realized this. Sometimes they give out the K for ammonia. I will still give this away naman because I didn't ask for you guys to memorize it. But the ammonia, for the K of ammonia is 1.304, apparently. Okay, anyway, right? If right, if your substance is any one of these 3, right, go ahead and use them, right? If they are not one of these 3, then go ahead and ask me, right? And if you want to be very pedantic, this 1.4 is exact. This is actually 7 over 5. You can replace that with 7 over 5. And the 1.667 actually continues infinitely long. So this is actually 5 over 3. Okay, anyway, right, that is our K, and right, our work non-flow formula is P2V2 minus P1V1 over 1 minus K. Right, so let's write that down now. P2V2 minus P1V1 all over, all over 1 minus K. What will this be? Right, I will now say that this is one of the most time-consuming integrations, but whatever, right? We have time. Rather, you guys are just in for the ride, right? Isentropic processes, your S is constant. We will have PV raised to K, right? K is constant. Notice that I am now shying away from the cursive because things will get a little dicey, right? This means that your constant is actually just your P1V1 raised to K, right? P1V1 raised to K. That is also your P2V2 raised to K. All right, now let's write down our work steady flow equation again. Negative P1, P2, V dP. Now, we're going to have to find our V. But the thing about the V is that, say, for example, if I divide P on both sides, you will have VK. V raised to K is equal to constant over P. We're not done yet because this is still raised to K. So we will need to raise both sides to 1 over K. Why is that? Because of the law of exponent, right? If you're raising A raised to M to another, right, exponent, you're just multiplying their, right, their exponents. Okay, so now your V is now equal to right, is now equal to constant raised to 1 over K divided by P raised to 1 over K. And this kind of looks like an eyesore, so what I will do is I will just put the constant, or put the P above. What I will do in exchange is that I will now write down P raised to, right, negative 1 over K. Right? Because of the negative exponent, you can just translate this back and forth. Okay? Why am I doing this? Because I want to put this value of V into this integral. So work steady flow is equal to negative from P1 to P2. It's now going to be constant raised to 1 over K times P raised to negative 1 over K dp. Notice what you can do is you can get that constant out of there, right? And what you can do with this, because this is just p raised to some exponent, you can apply the reverse power rule, right? The reverse power rule basically states that, let's move out the constant first, negative constant raised to 1 over k. The power rule basically states, the reverse power rule basically states you're going to have to add 1 to your exponent, and then you're going to have to copy that exponent down here, right? Down here. This is now from P1 to P2. Okay, now what, right? Excuse me. We can do a lot of things in here. First and foremost, what I need to see, or rather what I need to address first, is that isn't this working in the language of the arbitrary constants, right? Because, right, if you guys have gone through your integral calculus, right? Say for example, you have, or maybe even your differential equation. Say for example, you have an integral on one side, you have an integral on another side. What happens is basically you get an answer from here and you add a plus c if this is indefinite integration, and then in here you get another, right, answer, and then you add another arbitrary constant. But then your professors tell you actually you only need to add one, because, right, if you put this thing, say for example, if you put d to the other side, c minus d is basically just telling yourself, well, this is just a constant, this is another constant. If you subtract them, well, honestly, what just comes out is another constant. So the thing about this is now is that there is a little language that you're supposed to learn when you're in Cal Ing 3, that, oh, okay, say for example, you encounter, I don't know, c plus 5. Well, c plus 5, a constant plus 5 is just another constant. So in other words, it kind of just eats up the plus 5, right? Say for example, 2 times a constant, well, it's just another constant. It kind of functions like infinity if you think about it, right? But yeah. Say for example, e raised to c, right? E raised to some number is just another number. Ln of c is just another number, right? Sine of c is just another number. So why am I keeping, right? Why am I keeping, say for example, c squared is just another number. Why am I keeping this 1 over k in here? Does that matter, right? Does that matter as an exponent? Yes, because we have very explicitly stated from the very beginning, right? From the very beginning, that your constant in here is equal to either P1 V1 raised to k or P2 V2 raised to k. Now we have to understand what that constant raised to 1 over k now means. What if you raise everybody to 1 over k? You'll now have P1 raised to 1 over k, and notice that your V1 is raised to k, and then you raise it again to 1 over k, it will cancel out. Very interesting. P2 raised to 1 over k times V2. Now what? Okay, now at the very least I understand, okay, that's why I need to keep the 1 over k. Now what? Right? There's another thing in here that we can do. Notice that this 1 over 1 minus k is actually just a constant, right? You don't have to substitute anything to get here. So what you can do is actually you can pull out the 1 minus 1 over k at the bottom. So what we can do is negative constant raised to 1 over k all over 1 minus 1 over k. And now what you will just see in here is you can substitute your value of P2 and P1. P2 raised to 1 minus 1 over k minus P1 raised to 1 minus 1 over k. You will have this, and it sounds, or it looks all gnarly, right? And so what we can do is we can make a couple of adjustments. First and foremost is changing this, right? Let's make it into just one solid numerator. And what we can do is actually we can think about this as this 1 minus 1 over k, right? And notice that you can just represent this as k over k. And so we can put them together. We will just get k minus 1 over k, right? This will now become k minus 1 all over k. And notice that there is now a fraction in your denominator. What you can do is flip that so that the numerator is the denominator, denominator is now part of the numerator. So you'll now have negative, and I will bring back the the cursive, right? Finally, things are easing a little bit, right? Negative k over k minus 1 times your constant raised to 1 over k times this thing, p2 raised to 1 over 1 minus k minus p1 raised to 1 minus 1 over k. What I will do is the same thing we've done before. We will we will distribute our constants to both terms right here. And what that will do essentially is, well, the same thing, almost the same thing that we have seen earlier, right? Okay, there we go. And then what we will do is constant raised to 1 over k times p2, right? 1 minus 1 over k minus constant raised to 1 over k times p1 raised to 1 minus 1 over k. Now, we just defined earlier what constant raised to 1 over k now means. Either it is this one for state 1 or this one for state 2. So let's now replace our constants raised to 1 over k. This one, I can replace it with the definition for state 2. That is now p2 raised to 1 over k times v2. In this case, we can now replace this with a definition for the first state, which is p1 raised to 1 over k times v1. Now, what will happen? We will get negative k over k minus 1, right? K minus 1 times, notice what happens, p2 times raised to 1 over k times v2 times p2 raised to 1 minus 1 over k minus p1 raised to 1 over k v1 times p1 raised to 1 minus 1 over k. Notice that both of these things have the same base. Both of these things have the same base as well. So if they have the same base and they are multiplied to each other, what you can do is basically add the exponents. And in this case, adding the exponents means 1 over k plus 1 minus 1 over k. You are essentially canceling this and this part. You're essentially canceling this and this part. And you will be left with the formula for the steady flow work, which is, oh, not yet. There's one final flourish. Negative k times, negative k times p2 v2 minus p1 v1 all over, right? Oops. All over k minus 1. And the final flourish is removing this negative sign. What we will do is force it inside of this denominator. That means that your work steady flow for an isentropic process is going to be k times p2 v2 minus p1 v1 all over, right? Oops. All over, we will now reverse, right? The k minus 1, we will now go 1 minus k. That is your steady flow work. Okay. That's a lot of work. But yeah, that is now our steady flow. Okay, now notice, interesting, right? If you are not noticing yet, right, you should start thinking about, there's a lot of formulas that I'm gonna have to memorize, right? So think of just, a simple, how am I supposed to say this? Think about what these two, what these two columns are supposed to mean, okay? Think about why I am tabulating them in the first place, right? Now we go to isometric processes, the very kooky one, right? The very interesting process. And hopefully, when you see this process for a closed system, you're like, yes, finally. The thing about this is that this has a polytropic index that is approaching infinity. And the interesting thing about that is that because of the same thing earlier as the what do you call this, as the isobaric process, because the v's are the same, the vi and the vf are the same, well, your integral is just 0. So in this case, it's just 0. And so now, what is it here? Right? It's a very interesting question. We will now go and just finish this off in here, isometric. We'll have volume is constant, right? We will now have your PV raised to infinity, blah, blah, blah. What this basically means is that your V1 and your V2, excuse me, are the same. Let's call that a common V. And now if we see this, your work steady flow is just going to be equal to negative VDP. This is from P1 to P2. And now you notice, wait a second, your V is constant. It's literally constant. You can just bring it out, right? Negative V times, wow, that is a very hard integral. No, it's not. It's just the integral of dp, which is just p. And now you get to a very simple conclusion. Your work steady flow is now your negative v times p2 minus p1. Very simple conclusion. Okay? That is your work steady flow. Right? So now you're seeing, wait a second, this looks like an isobaric process from earlier. It's just that they switched places. Very interesting observation, right? You are definitely correct in there. It seems like they just switched places. Very interesting. And now, right, we don't even have to go through the slide for the polytropic process because we've already done the work from earlier, right? If you just replace the k with any kind of n, right, you will still arrive at the same thing, right? So let's just replace all of our k's with our n's, and we should be fine. P2 V2 minus P1 V1 all over, all over 1 minus n instead of 1 minus k. You will turn this into, right, I will copy from here. We will have n times P2 V2 minus P1 V1 all over, right, all over your 1 minus n, and we should be done. This is now your full table, shall we say, right? This is your full table for the process, the kind of polytropic index, the work non-flow, and the work steady flow. Why did I do this? Right? Why did I do this? The thing is to illustrate to you, right, that, well, now that this is all over, right? There are no more new formulas, okay? There are no more new formulas. You might say to yourself, there are so many, right? Just so we get a full kind of recap, right? For work non-flow, there's a general formula, right? The general formula for work non-flow is basically the integral of PdV from your initial velocity, from your initial volume to your final volume. The work steady flow also has its own formula, the one we just saw earlier, negative VdP from your P1 to P2. So you may say to yourself, the full list, or rather the full number of formulas that we're going to have to memorize is the general one for non-flow, the general one for steady flow, and notice you have essentially 5 for non-flow processes, right? 4 if you don't count isentropic and polytropic as different things, right? But 5s, let's say for example 5, that bumps the total to 7. And then you notice, wait a second, I can use the ideal gas laws with the work non-flow processes, and you will get another 5, so that's a 12. And then I'm giving you work steady flow, which is another 5, that's 17. And then I will tell you right now, you can also use steady flow works with ideal gas laws, and that is another 5. You will bump it up to 22. So essentially, if you are doing this at a very brute force manner, you're going to have to memorize 22 different equations. That is hell. I do not want to do that. I'm not a med student for me to have like unlimited amounts of, I don't know, memorization power, right? I came here in engineering because I just want to compute. I don't want to memorize, right? Hopefully, a lot of people resonate with that idea. And so I will tell you right now that I'm doing this deliberately so that I can show you that there is a relationship that ties it all together, right? In topic 2, or rather in quiz 2, before quiz 2 happened, I told you guys that actually for all these 5, right? For all of these 5 in here, you only need to memorize 2. Memorize this and this. Why? Because, right, this actually takes care of everything. if this is an isobaric process, your N is 0, and this is your isobaric process. It's just that the P2 and the P1 are the same, so you can group it out. This is your isobaric process. Next, right? For an isentropic process, replace the N with a K and then you're done, right? For an isometric process, replace the N with an infinity. 1 minus infinity is negative infinity. Well, negative infinity, if that is your denominator, well, it's going to be a 0. And then finally, why did I ask for you guys to memorize this thing? It's because this is the only thing that breaks, right? This formula, right? If your N is equal to 1, that gives us a division by 0. And notice that if, right, this is an isothermal process, then P2 and P2V2 and P1V1 are actually the same. So you will have a 0 over 0, which is L'Hopital's rule. But you know what, the consensus here is that you can just memorize the isothermal process. So technically, you only need to memorize 2 out of the 5, right? And honestly, if you know that any PV can be replaced by an MRT because of the ideal gas law, if your substance is an ideal gas, you don't need to memorize the another 5, right? If anything, just memorize PV equals MRT, and then you're good, right? The thing here is that there is a relationship between non-flow and steady flow work, right? Non-flow work and steady flow work are related by this relationship. N times your work non-flow is your work steady flow. Look at this. N times your work non-flow is equal to your work steady flow. Look at this. You multiply all of this by 0, you will get 0. Cool. You multiply this by 1, you're not changing it. It's the same, right? That is why I deliberately gave you guys the kind of the complicated version, right? The complicated version wherein I was supposed to say that this is the formula, but then I was prompted to prove that these two forms are the same thing, right? This is for this reason, right? This is for me to tell you that, well, you're just multiplying by 1. Nothing is changing, right? Notice that for an isentropic and a polytropic process, right? If you just multiply any value of K or any value of N, it's the same thing, right? K times this is literally this, right? N times this is, again, this thing, right? The only thing, again, where this breaks is the isometric process, right? Notice that infinity times 0 is a kind of an indeterminate form. So again, L'Hopital's rule, right? But for me, how this is solved is if you know that your N times your work non-flow is equal to your work steady flow, you can reverse engineer it and say that your work non-flow is just equal to your work steady flow divided by N. Notice that in this case, if you divide this by infinity, yes, it will indeed be equal to 0. Okay, so that is the justification here. And honestly, that's it, right? That's it. Right? If you understand or if you remember that this is true, well, then you are able to recreate most of the steady workflow formulas, steady flow work formulas. Maybe the only thing that you can't reconstruct is this, right? So just memorize that. So from 22, we are down to, I don't know, 10 maybe, right? Less than 10. Thing about this is that if you are smart, right? If you are smart in how you're able to absorb this information, if you're able to understand, oh, this is not necessary. Oh, this can actually be simplified. Oh, there's another form that makes it easier for me to understand. I feel like that's the way to success, right? And so that is the end of the first part. At the end of this first part is for us to understand, for us to realize that your N times your work non-flow is your work steady flow. And from there, we are able to tackle the different kinds of steady flow devices, right? So if you guys have any questions, please let me know either in the comments of this video or maybe just message me on Canvas or on email, whatever, right? But that is the coverage for this first part, right? Next part, we will go and think about steady flow devices. The first part will be for pipes, nozzles, and diffusers. So I will meet you guys there. Thank you.